My name is Jonathan Fortney. I'm the department chair in the Department of Astronomy and Astrophysics here at UC Santa Cruz. Thank you all for coming to the Mandel lecture. For many decades, we've been running public lectures in town to try to bring some of the state-of-the-art astronomy that we're doing in our department to Santa Cruz. And for quite a few years now, we've been doing that at the Rio Theater. Steve Mandel and Carol Foote have been generous enough to support the lecture series over the past several years, and you'll hear more about them in a few minutes. At UC Santa Cruz, we seek to understand the universe through cutting-edge research and also through education of undergraduates and graduate students, and also through making connections through the public in Santa Cruz County and beyond. So after me, who'll be speaking first will be the Dean, Brian Gensler. Brian is an eminent radio astronomer who joined the UC Santa Cruz a couple of years ago after having previously worked at Harvard University, working in Australia, and then moving on to the University of Toronto. He's a very eclectic astronomer who's worked all over the world. We're lucky to have him in Santa Cruz. He's the Dean of our Division of Physical and Biological Sciences. And then we'll hear from Steve Mandel, and then we'll hear from Bob Williams. Bob will be talking with us about one of the most momentous feats, I would say, in the history of astronomy, the Hubble Deep Field Image that showed us how full our universe really is in seemingly empty space. So thank you all for coming, and first up will be the Dean, Brian Gensler. Thank you.
Well, good evening, everybody, and welcome to this year's Mandel lecture. It's amazing to see almost completely full house here. I'm glad to know that space has such a special resonance for you, and tonight you're in for a real treat. So tonight is about the Hubble Deep Field and celebrating its 30th anniversary. And this particular field has deep resonance for me. I remember when it came out, I was a student, and there was this just nothing but galaxies, and in the little left-hand corner in tiny little writing, it said R. Williams. And I always just thought, who is this R. Williams, and who had this idea? And tonight you're going to hear all about it from R. Williams. So a number of years ago, I wrote an essay on the Hubble Deep Field, and Steve Mandel, our host, told me that it meant a lot to him, and Bob Williams said he appreciated it as well. So I thought that the only way I can do justice to the speakers that follow me is just to read a short excerpt from my essay. And while you're listening to me, that is the Hubble Deep Field on the screen. And so this is what the essay is about. So the most important photograph ever taken was a picture of nothing. The Hubble Space Telescope, which for the last 35 years has orbited 320 miles above our heads, was until recently the most powerful observatory ever built. In late 1995, Hubble took a break from looking at the usual assortment of stars, planets, and nebulae, and instead devoted 140 hours, spread over 10 straight days, to staring at a tiny, nondescript part of the sky in the constellation of Ursa Major, the Big Bear. Hubble's field of view is minuscule. Each exposure covers an area on the sky less than 1/100th the area of the full moon. And this particular little patch of the sky had been carefully chosen to be as uninteresting as possible, containing just a few faint stars. So what did Hubble see at the end of this mammoth 10-day exposure? Well, a handful of stars, there's a couple of them in that picture, but filling the space between the stars, as you can see, is a riot of smudges and whirls, all of different colors and sizes. And what are all those smudges that you can see? Well, appropriately, it was Edwin Hubble himself who figured out the answer more than 100 years ago when he showed that each of these faint patches was an entire galaxy, each containing hundreds of billions of stars. I want to say that again, hundreds of billions of stars, each one of those smudges. So let's put this in perspective. Our home galaxy, called the Milky Way, contains around 400 billion stars of various temperatures and sizes, and it spans about 1 million trillion miles from side to side. Now, as mind-boggling as that is, the Milky Way is a very average galaxy. It's completely dwarfed by its neighbor, the Andromeda galaxy, which is 15 million trillion miles away and contains another trillion stars. And the Milky Way and Andromeda are both part of a much larger grouping called the Virgo supercluster, which consists of thousands of galaxies spread across more than 1 billion trillion miles of space. So the light that distant galaxies like the ones in this picture emit, which are eventually received by the Hubble Space Telescope, that light travels at a very specific finite velocity, the cosmic speed limit, the speed of light, 670 million miles per hour. So it therefore takes time for this light to reach us. And we're not just talking like a slight delay, like a conversation on a bad phone line, but a wait of billions of years. So the night sky is a time machine, and the galaxies in the Hubble Deep Field are what our Milky Way galaxy might have looked like when it was much younger than it is today. Using the smudges and colors in the Hubble Deep Field, astronomers can understand how galaxies, the building blocks of the universe, how they formed and how they've since evolved. There are few questions more profound than how we got here, and through the images like this one taken by Hubble, we've gone a long way toward answering this question. Even hardened scientists like me cannot help but feel dwarfed and humbled when we contemplate such issues. The universe is bigger than we can imagine, it's older than we can contemplate, and more complex than we can conceive. All our dreams, our fears, our times of triumph and of sorrow, our sense of history, our hopes for the future, well, they're all utterly irrelevant and insignificant when contrasted with the colossal dance that galaxies play out as they drift and spin through billions of years. Our world could end tomorrow. These stars wouldn't notice. The Hubble Deep Field, as much as a great work of art or a multi-layered symphony, symbolizes humanity's achievements. Tonight, as we celebrate the 30th anniversary of this extraordinary photograph, this marvelous gift that Dr. Bob Williams has given to all of us, the story comes full circle. Born of stardust, billions of years old, having existed as a species for just 0.001% of the age of the universe, and animated by a mere 3-pound bundle of fibers and electrical impulses sitting inside our skulls, we have the capacity both to photograph the full complexity of the night sky and to transform these scientific measurements into an aesthetic expression of grandeur, wonder, and beauty. So that's my reaction when I look at this photo. You're going to hear multiple different reactions tonight. Oh, thank you, sir. Thank you. I'm just the warm-up act. You're going to hear a lot more. So it's my great pleasure now to introduce my colleague and friend, Steve Mandel, the sponsor of the Mandel Lectures. So Steve is a long-term donor, supporter of the campus, and a former employee of UC Santa Cruz in the early 1980s as director of the Institute for Computer Science and as a University Extension Program Director. Before he retired, Steve founded Mandel Communications, providing training and consulting services to science and technology companies around the globe. Steve, along with his wife Carol Foote, who's also here tonight, have supported the sciences through the annual Mandel Lecture in Astronomy. And Steve has served as a mentor in the Osterbrock Leadership Program for Astronomy and Astrophysics grad students and postdocs for 10 past years. And he's also a research associate at UC Santa Cruz's Department of Astronomy and Astrophysics. Steve has a great passion for science and conservation. In 2007, he established the Lions of Gir Foundation, a non-profit to address the needs of the critically endangered Asiatic lions of the Gir forest in India. He's also an award-winning wildlife photographer, with his work juried into the Smithsonian Natural History Museum for public display. Steve's foundation then went on to operate 2 additional programs: Oceans 360, providing underwater 3D virtual reality videos for ocean conservation education, utilizing a camera system of his own design that was also used by National Geographic, and Oceans Micro, which live streams life in a drop of seawater to students in biology classrooms. For 2 years, Steve also had a lab at the California Academy of Sciences, helping to identify fossil microorganisms, diatoms, from the historic collection of microscope slides. Steve's an accomplished amateur astronomer, and in 2005 established a robotic observatory in the mountains of New Mexico, where he photographed previously unseen details in unusual dust clouds at the very edge of our galaxy. Working with a team of astronomers, he was co-author on papers in the Astrophysical Journal and was awarded the prestigious Chambliss Award for his work by the American Astronomical Society. Steve's photos and articles have appeared in NASA publications, Smithsonian books, Sky and Telescope magazine, Astronomy magazine, Forbes, the New York Times, and other domestic and international publications. Currently, he and 2 other amateur astronomers operate the Deep Space Remote Observatories with telescopes in California, Chile, and Australia, and he's going to be telling you about some of the things the telescopes have seen in just a minute. So as I said, I'm just the warm-up act. There's 2 very exciting talks to come. Please join me in welcoming Steve Mandel.
Thank you so much, Brian. Can you hear me okay? Is that working? Good. All right. Okay, there's a picture without too much writing on it, and this is from Bob. So I want to thank all of you for attending this evening. And it's really great to be here to celebrate really one of the most iconic science images, but really just one of the most iconic photos ever taken. And when Bob proposed using his, I think it was something like 250 hours, he was director of the Space Telescope Science Institute, and so he got some discretionary time, a lot of time to do what he wanted with the telescope. When he proposed this, there were a lot of people who asked a question, and the question was, is Bob Williams crazy? Because he wanted to use all that time and photograph, as Brian said, nothing. Well, it turned out, of course, that he was not crazy, and we all learned a lesson from him about taking risks, asking bold questions, and not being afraid of being bold in seeking the answers to those questions. So about a year ago, I was talking to Bob, and I said, what year was that? He said, 1995, and he realized, wow, next year, this year, 2025, is the 30th anniversary of that amazing and iconic image. So along with asking Bob to give the lecture tonight, and inspired by what he did 30 years ago, I came up with the idea of asking amateur astronomers to turn their telescopes to different nothing patches, like dark patches between the stars, just to see what would happen, see what would be accomplished, truly in the spirit of let's look at nothing and see what we can get. So I created the Amateur Deep Field Project, and my telescope partner, Bob Farah, who's here tonight with his wife Janice, and we decided to use our telescopes. We have one up at a facility in the Sierra Nevadas, another one at a facility in the Andes in Chile, and then I asked a number of my fellow amateur astronomers if they would join in, and they did. And actually, a number of them are here tonight. They're sitting up in the front, and a lot of these folks flew in, and I think our record holder is Rafael, who flew in from Brazil, Rio de Janeiro. So thank you for coming. Obrigado. So we had one group of telescopes, about 10 telescopes in the northern hemisphere, and about the same number in the southern hemisphere, pointing at the same dark patch, nothing patch of sky. And the idea was to take the signals from each hemisphere and aggregate them, in other words, put them together, and produce 2 images, one from the northern hemisphere, one from the southern hemisphere. And I'm going to show you the results of what we got in a couple minutes here. The telescopes that we have are operated remotely by the people or organizations who own them. And this was truly a global effort because we had people from all over Europe, North America, South America, Australia, and Asia who participated in this project. Let's see if I can successfully change a slide here. And here's the team. We had over 30 people who participated in this, and I want to thank all of them very, very much. This is being recorded, so they will see this, and they know who they are. And a big shout out to, of course, Bob Williams for inspiring this, and also I want to thank Connie, who's a professor of astronomy here, for being willing to take my calls and listen to my silly questions and always give me wonderful information and answers. And to all of the participants, I thank you from the bottom of my heart, because this could not have been done without everyone pitching in. And you can see there's a lot of people, and a lot of people spent a lot of hours on this. And we have a website that'll be up, I think, towards the end of this week, amateurdeepfield.com, and there'll be more information and photos I'm going to show you on this project. Now, tonight, you're going to be hearing the words millions, billions, you already heard this a little bit, trillions, and million, billion, and trillion are difficult concepts. And to give you some perspective, 1 million is the number of seconds in a little over 11 days. If you don't believe me, start counting right now, don't stop. A billion is the number of seconds in 31 years. So you really better start counting on that one. And a trillion is the number of seconds in a little over 31,000 years. Now, I can't get my head around that, but I thought I'd share that with you. And let me boggle your mind a little further, because the other thing you're going to hear tonight is the term light year. Now, a light year is simply, the distance that light travels in 1 year. So how fast is light moving? It's moving at about 186,000 miles per second. It would undoubtedly get speeding tickets if it went over Highway 17. Now, at that speed, in 1 year, it covers about 6 trillion miles. I'd like you to remember that, because there will be a pop quiz at the end of the talk tonight on all these numbers. Okay, let's take a look at the first image, and this is from the northern hemisphere. Oh, sorry, I forgot this one. These are some of the telescopes that we used, and the next image will be the northern hemisphere image. And you can see that these are instruments that are, we have some of these scopes are in the Sierra Nevadas, some are in Chile. We have one in Utah. Kent, who's here tonight and traveled to be here, that's his telescope. And that handsome guy in the center there, that is Bob Farah, my telescope partner, and that is our 17-inch telescope that we were installing in the Sierra Nevadas at that time. Okay, here is the northern image. And this is an amalgamation of 10 different telescopes, the total of, as it says, 295 hours. And if you looked at this spot, and with our telescopes, you're looking at an area a little smaller than the full moon. And if you looked at this spot at night from a very high mountaintop on the clearest possible night, you would see nothing. You wouldn't see any of this. You wouldn't see the bright stars in there. This is only visible telescopically. And the telescopes, are able to see this, of course, because we're putting all this data together. And the remarkable thing about this is that it is not the bright stuff in the image, it's all the faint little dots. And if you see look for the faintest thing in there, somewhere, I did have a laser pointer. Oh, here it is. Give me a second. I mean, really look for these little, faint little dust specks. And as Brian said, those are galaxies. And if they're the same size as the Milky Way, they may be holding 400 billion stars in each of those little specks. And this is what we were able to achieve. Now, Connie helped me go through databases so we could identify what some of these things are and how far away they are. So for reference, this is a star in the Milky Way galaxy. And as it says, it's about 6,400 light years distant. And I want you to think of photos like this and the Hubble Deep Field as almost 3D, because we're seeing some things close in, and then we have intermediate objects, like that little galaxy, and I picked that one because you can see the shape, and that one is 842 million light years. And in searching through this, it was very tedious, but it was a lot of fun and exciting to identify these things. See those little red lines in the lower right-hand corner? That little object is 7.8 billion light years distant. So we were able to reach very deep with these images, and the image on the website will have even more annotation. If you're wondering what the numbers are in the galaxies, SDSS is the Sloan Digital Sky Survey, so that's for the astronomers, that's the reference in the catalog, and Z is the redshift factor. With the redshift factor, we can determine distance. If you look at this, and the one I'm going to show you in a second from the southern field, probably about 1% of the objects in here are stars in the Milky Way, and everything else are distant galaxies. And this was the magic. This is the amazing thing about the Hubble Deep Field image, that you looked at a blank spot, and the more we look, the deeper we look, the more we see. It doesn't disappear. It gets richer and richer and more interesting in the process. Okay, let's see here. Let's take a look at the next image. Okay, here is the picture from the southern hemisphere, and 291 hours was amalgamated from, once again, about 10 different telescopes. And, you know, it's very pretty. There's pretty stars in it. And what I want to do, because there's a lot going on in the center of the photo, and once again, if you were looking at this with your naked eye in excellent conditions, it would just be a black spot. It would be nothing. Let's zoom in a little bit, and we start to see some structures in some of the galaxies. And one of the things that's kind of pretty that I noticed when I zoomed in was a double star, once again in the Milky Way, and the bright stars have what are called diffraction spikes on them. It's an optical effect from our telescopes. Let me show you two other objects here. So there's the 12th magnitude star. And that little galaxy, that little corkscrew galaxy there, that one is 1.4 billion light years distant. And in looking at this image, as I was studying this and trying to figure out what's what and look at the survey data, I came upon this object. See the little red lines there? That little guy is 11.3 billion light years. The sun formed about 4.6 billion light years ago. This is way, way before the sun was here, the solar system was here, anything that we know. And when I saw this, you know, I was really excited by this. It's amazing, you know, to look at that and go, is that right? And I called some of the astronomers, and they looked at it with me and said, yeah, that's what's going on here. And after we had gotten all the images together, and I did this analysis, and I saw this, and I had an idea. And the idea was, and I called Bob Farah, and I said, hey, Bob, let's point our telescope in Chile at something else that I've just seen on a spreadsheet, and see if we can capture this thing. And probably not, but let's give it a shot. Now, before I show that to you, I want to talk just for a second about the Big Bang, because the Big Bang, the explosion, or whatever the proper term is, that created the universe, is thought to have happened about 13.8 billion years ago. I think the number is really 13.77, but let's say 13.8. And the current record for a galaxy, a picture of a galaxy, was actually taken just about a year ago by a team led by UC Santa Cruz scientist Brant Robertson. And he was able, using the Webb telescope, to image a galaxy that was 13.4 billion light years. You know, which is, yeah, that's just amazing, unheard of, but now we couldn't do it without the Webb. So I thought, okay, well, let's see what we can do with our little telescope in Chile. And so this is a zoom in of an image. Now it's not a pretty picture necessarily. It's just a black and white, and we have a nice color image of this field. And I saw I looked at the database and I said, what's the dimmest thing on this database? And I said, let's go after that. What the heck? And my what the heck was really based on the spirit of all these amateur astronomers when I called them and said, let's look at nothing and use your precious telescopes to photograph nothing. And look what we came up with. And that goes back, of course, to Bob Williams' experiment of let's use the Hubble Space Telescope and look at nothing. So I said, well, let's look at this thing just in the spirit of adventure. And so we captured light that traveled 13 billion years. This is when the universe was, I think, 8% of its current age. And we have a 17-inch telescope. This thing turns out to be so bright that we captured it in a single 15-minute exposure using a clear filter, which I just couldn't believe. And it opened a whole world to me. And I'm going to be publishing this, and I've got a list of other 13 billion year quasars that I'm going to make available to my amateur astronomer friends globally so they can have this fun and marvel at this stuff. So quite possibly what we got here, I'm not 100% sure, but possibly, this is the deepest image ever taken by amateur astronomers. And so I'm happy to say that, well, thank you. This is in the constellation Virgo, and a lot of amateurs have photographed this area, and I bet they've captured this and just thought it was a star or just nothing. We'll find out. But if it is the case, then UC Santa Cruz holds the record, both the professional and amateur record, for the most distant object photograph in the universe. I have to say this, go banana slugs. So one more thing we did here, and this is unofficial. This is a nickname, but as I was doing this, it all goes back to what Bob Williams did 30 years ago. And so we've nicknamed this quasar Bob's quasar. So Bob, it's not SDS or gamma, blah, 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 blah. I'm going to always think of this one as Bob's quasar. And it's really to honor the spirit of courage to take this on, a curiosity and exploration. If he didn't have that, my God, we wouldn't be having this talk. So I want to thank you, Bob, for the amazing thing that you did that will last eons. Literally, billions of years. And Bob's quasar is going to be there a long time also. And thank you, audience, for coming to the talk tonight. So now I would like to invite to the stage Sandra Faber. And Sandra is a professor emerita at UC Santa Cruz in the UC Santa Cruz Astronomy Department. And Bob also, if you would both come up, and Sandy's going to introduce Bob Williams. So please come up to the stage.
Thank you, Steve.
You're welcome. So I've got your first slide up there.
Hi, everybody. Bob, why don't you come and stand next to me here? Okay. So, as noted, I'm Sandy Faber, and I'm a professor emerita in the astronomy department. And it's my great pleasure to introduce tonight my friend and colleague, Robert Williams. Robert is an amazing guy, and he's going to tell us a wonderful story. We're in for a treat. We're going to hear the unvarnished strategic planning that went on behind the scenes and the political discussions, pro and con, about whether this image should be taken or not. In my opinion, this is the most important, significant image ever taken by a human telescope. Why do I say that? I have to sort of set the stage for you. Maybe you'll do more of this, Bob. You have to realize what astronomers were thinking about the beginning of the universe and the formation of galaxies when this image was taken. We were still in the midst of a controversy. There were a lot of people around who espoused something called the steady state theory, which said that essentially the universe never had a beginning and kept sort of remanufacturing itself, such that if you looked out in space, it would always look the same to you, no matter how far you looked. This image is, I think of it as a core drilling out in space, but also back in time. And in this single image, it tells the story that the universe had a beginning, that galaxies were different in the past. There were infant galaxies, there are mature galaxies today. It took us a few years to read and decode this image, but we did. And it's just had an incredible impact on astronomical thinking, cosmology thinking ever since. Bob was trained, I like to say, as a classical astronomer, and by that I mean he's a spectroscopist. Have you ever wondered, when you read these articles in the newspaper and they say this thing is made out of nitrogen and oxygen and it has a temperature of so many degrees and, you know, it's dense or it's not dense, how much does it weigh? How do we know all that stuff? Well, the theory has been worked out and it's hard to understand. It's hard for me to understand, but experts like Bob have made a science and a career out of looking at these faint signals in spectra. Oh, it's bright at this wavelength, but it's not bright at that wavelength. What does it mean? He's the guy who deduces what's really happening out there. He's also an amazing person, takes risks, and I think maybe the first big risk that I know about is he's the only person I know who actually turned his back on a tenured professorship and walked out into the unknown hoping to find something else to do. And in the process, I think he really found his niche. He became director of the Cerro Tololo Observatory in La Serena, Chile, which is the southern station of the National Science Foundation. And he was director there for 8 years, taking risks, looking to the future. He just told me a couple days ago that it was he who purchased the land on which the Vera Rubin Observatory is now being constructed. Bob describes those years in Chile as perhaps the sweetest of his career, but family called back in the United States, and so he and Elaine removed back up north, and he took the job at the Space Telescope Science Institute in Baltimore in 1993. Now, again, setting the stage a little bit, you need to know that the Institute was really in turmoil at the time. Hubble had been launched in 1990 with the optical flaw. It had just been repaired, and it was still finding its feet. Yes, those pictures from the refurbished telescope were impressive, but you know, there had been an awful lot of bad press, and NASA looked bad. So it was a delicate moment, and it took a lot of courage to put a huge amount of director's discretionary time into this gamble of an image, would it show anything or not. Bob has received many accolades in his career. He's received the Tinsley Prize of the American Astronomical Society, the Carl Schwarzschild Medal. He's a member of the American Academy of Arts and Sciences. But Bob, we'd like to add one more accolade to your long list tonight. Perhaps our audience doesn't know, and I will explain, how astronomical objects get named. It's not true, though you may think, from advertisements that it's possible simply to buy a star and put your name on it. No, in fact, there's a whole process for naming astronomical objects. And it's my pleasure to tell you today that there is now asteroid Robert Williams. Let me read from this certificate which we prepared. Says the International Astronomical Union Minor Planet Center, and it says, Minor Planet 359474 is hereby named Robert Williams. The discovery in 2004 by Larry Wasserman, and you're very pleased, your telescope at Cerro Tololo. Okay. There's a map on here that shows a map of the solar system and the location of Robert Williams at this very moment. And here's the citation. There's always a citation that's attached to this. It says, Robert Eugene Williams, born 1940, is an American astronomer who directed the Space Telescope Science Institute from 1993 to 1998. It was his decision to take the Hubble Deep Field image, which captured infant galaxies 12 billion years back in time, and which showed conclusively that the universe is evolving. Here you go, Bob. Here, you can look at this later. Okay, take it away, Bob.
Thank you, Sandy. And I was president of the IAU once, knew nothing about this. Good evening. Great to be here. 30 years ago, a group of 17 scientists, most of whom were young, and did not have positions longer than 2 or 3 years at our institute, gathered together and commandeered Hubble Space Telescope for a period of 10 consecutive days and nights. We took image after image of what you've just heard from the previous speakers, of an undistinguished area of the sky where nothing had been studied. There were relatively few stars in the Milky Way that were in the way in the beam of the telescope because we wanted to see further than that, and took image after image for the 10 days, 345 straight images. Telescope never touched it, never moved it. And so you may wonder, why not take just one single image? And the answer is, the CCD instruments on Hubble telescope, that are the same as in your cell phones, can take exposures, at least for the instruments on the Hubble, only about 45 minutes or so before the electronic noise in them comes up and basically produces a background, of course, that gets in the way of what you're trying to image. So the fact is, if you really want to take a long exposure, the way you do it, certainly on the Hubble, is just take image after image. And what we're trying to do, of course, is achieve an image where we could detect the faintest possible objects possible. We did it in 4 different filters: ultraviolet, blue, green, and red. And the reason we did that is because that use of the filters would tell us whatever the objects are that we happen to image, and of course we didn't know that, at least their relative brightness in the different filters would give us an indication of exactly what type of object they were. In addition to which, it did not escape the attention of the director then, that if we failed, basically, to detect anything, at least it would produce a nice, pretty picture that we could show. And that, we can laugh at that, but since astronomy is a pure science and we must put it before the public, it was really important to us that at least we had an attractive picture. And in fact, there were few astronomical photos or images at that time that were produced in color. So we spent days after the 10 days, about 2.5 weeks, reducing the data. It was a huge amount of data, so that we could present it to the public, which we did in a meeting of the American Astronomical Society in San Antonio. This is in early 1996. And release it to the public and the scientific community. There was a considerable amount of interest, of course, in that image. And you've already seen it now. And we named it the Hubble Deep Field. The reason, it was taken with Hubble telescope. It was deep because we tried to detect the faintest objects that we could. And it was a field because there was no particular object that was in it that we knew had been studied before. And in terms of the use of the filters, for example, we can tell you what one is seeing in that image. There are a couple of stars, and here is one, and here is another. There's a red star there and a blue star there. And simply the difference in the colors tells us, and we weren't particularly interested in these stars. This is probably a massive star, whereas this is a star that's less massive, and it's cooler, and therefore it radiates more in the red than in the blue. So you actually have information about that. But it wasn't the stars that we were interested in. In fact, it was the galaxies. And there are 9 stars in here from the Milky Way only, and everything else that you see here, and again, both Brian and Steve have mentioned this, they're galaxies, each consisting of tens of billions of stars. Some of them are large and fairly bright, presumably close. Others, of course, are very faint. You can just see them little specks here. So there are 3,000 of them. And as, again, you've heard, the size of this field was the size of a pinpoint held at arm's length. So it was a teeny speck of the sky. And so the fact is, what was there of interest in this picture, actually, other than the fact that we were able to detect scads, loads of galaxies? And the answer, and why was there such interest in it? Such that even 30 years later now, we're wondering, well, what is it about this image? And the answer is, this one image was our attempt to reveal the contents of and the evolution of the universe. No small problem. So the fact is, and again, you've already heard part of this, it's a simple concept that enables us really to understand how it is that this two-dimensional picture can actually tell us something about the universe. And in order to do that, we need to say something about the telescope, which took the image, and then several concepts that, again, I'll explain to you, and you've already heard something about them, about what it is that we see when we look up at the night sky. First of all, the telescope. It's been there since 1990, orbiting every hour and a half at an elevation of 600 kilometers. That's about 360 miles. Taking observations night and day. So the one thing about Hubble Space Telescope that makes it so important is just really one thing. It has many other very good characteristics. It's above the Earth's atmosphere. The Earth's atmosphere is, it's great for sustaining life. We need the air, but for astronomy, it's a pain. It distorts the light that we see and blocks out large parts of it. And so if you really want to do astronomy and understand the universe, you want to do it above the Earth's atmosphere. The one drawback, obviously, is it's expensive, and we're very aware of that. But it does produce wonderful results. So the telescope really produces excellent photos, and here's an example of a ground versus space-based image. of a gas cloud that's actually in one of the Magellanic Clouds that you can see, taken from the ground with an 8-meter telescope, and that's a mirror about 20 feet wide, compared with Hubble Space Telescope, which is a 2.4 mirror, 8 feet wide. So Hubble, much smaller telescope. But look at the background here, much darker above the atmosphere than you have below the atmosphere. And look at the ability to image both bright and faint things. That is, you see all of these stars right here, and here from the ground, you don't see them. So really, space is the place to do astronomy. So that's the important thing. As far as the universe, what we need to understand is two things. First concept, when you're looking out in space, you're looking back in time. And this was really the theme of Dean Gensler's essay. So the typical distance between galaxies is about 1 million light years. And so let's say if the Milky Way was represented by this particular galaxy, when you look out here, you see these galaxies as they were when the light left them, and it's earlier and earlier for the galaxies that are further away. And so the fact is, really important in astronomy, archaeology, paleontology, great things, but they have to study artifacts. In astronomy, the only science in which you can truly actually look into the past. Now again, if you think that the universe is the same at all times, there isn't such a great interest in looking into the past. You just figure what's like the present. And so it is the second concept that made that such an important thing, as Sandy was just saying. The fact, the other concept is that all galaxies are expanding away from each other. This was the great discovery of Edwin Hubble and a Belgian astronomer, Georges Lemaitre, in the late 20s. And I'm giving dates on some of these things because I want to present this to you in sort of a historical context. So a century ago, and I can show this if I can manage the pointer here. Not using my own laptop, so I can't get it, so it goes, we can live without it, I guess. Oh, but I'm going to need this for another video, which you really have to see. Well, let me come back to that. In any event, the important discovery of Hubble and Lemaitre was when they looked out at distant galaxies, they basically had velocities that were such that,
see it over your shoulder.
So I don't, okay, so I see it there and not in here. Thank you. Okay, so I shouldn't come. So basically, the universe is expanding, and it's expanding uniformly. It wasn't just that several galaxies happen to have movements away from us. The universe is full of galaxies in a uniformly expanding space. And this discovery was transformational because it indicated that the universe was in evolution. And believe it or not, that was an important concept a century ago. In fact, a century ago, it wasn't realized that there were even other galaxies than our own Milky Way galaxy. Telescopes, even the largest at the time, felt that these little fuzz balls that one could see were actually gas clouds in our own galaxy. So tremendous difference in thinking a century ago. There are other systems containing billions of stars, and in fact, they are all expanding away in this expanding space. So, important concept. If it's expanding, you project back and say, hey, things are moving away now. They must have been closer then. And you deduce that there must have been a beginning. And so the fact is, about a century ago, there was this concept that the universe began, this present universe began at a certain point that we call the Big Bang because it was clearly full of energy. And we can determine, simplest equation in your elementary physics is distance is velocity times time. And so you can determine from the velocity of the galaxies that are expanding, from each other, exactly what that time was, and the Big Bang occurred 14 billion years ago. I should say that space is expanding, but the galaxies themselves are not expanding because they are bound by gravity. So the Earth isn't expanding, bound to anything that is held together by gravity is not expanding. It's the space between them that is expanding. So this concept of an evolving universe, which means probably the things were different in the past, and there was a beginning. So the initial cosmology, very simple in projecting back in time, can be represented in this figure here, where we're taking time, evolving from left to right. We're looking at ourselves here 14 billion years after, and projecting backward to this point in the Big Bang. So generally, not just the public, but even myself, an astronomer, ask the question, okay, interesting, what happened before the Big Bang? And how did you get all that mass together in something that's so compact? And in an infinite universe, what are we talking about? Okay, I've got partial answers for some of those, but a don't know answer for what happened before the beginning, all right? So we can project back to the beginning, Big Bang, and if you ask what happened before that, the answer is don't know. Science addresses those things about which we have facts. At the moment, we have no known facts that tell us anything about the state of the universe or whatever preceded it. I personally believe in the next few generations that we may find some processes that will be able to tell us what happened before the Big Bang, if there's a concept there. Because the fact is, how can anything have a beginning? In our finite minds, there's one concept that we all have a difficult time grasping, and that's infinity. How can there ever be a beginning? There was always something before that. How can the universe be infinite? And so I personally am not able to handle that very well, other than mathematically, when you build models, we can do a representation that predicts observables that we can test our theories with. In any event, Big Bang, it was probably energy only. So for those of you who wonder, how can all of this gotten together in such a compact form? Remember Einstein's equation, E equals mc squared. Energy equals mass times speed of light squared. Energy and mass are the same thing. They're interrelated. You can create energy out of mass, right? Nuclear energy. You can take mass, change it, and you get energy out of it. Vice versa. You can take some mass, an electron and a positron, bring them together, they annihilate, and they produce radiation. They produce energy. So what we think is the Big Bang was energy only, and the tremendous energy right after the Big Bang, and I could give you, seconds, microseconds or whatever, all the particles, the forces of nature that we know about, electricity, magnetism, nuclear energy, they were produced after this tremendous energy at the moment of the instant of the Big Bang, and this huge inflation that occurred. In any event, so here's a simple cosmological picture, okay? 14 billion years, we've got the start, don't know what happened before, I'll keep saying that. But what we know from thermodynamics is anytime you take a gas and you compress it, it heats up. Anytime you let a gas expand, you know that it cools down. So one of the inferences of astrophysicists is, here we are, we can observe with our telescopes what things are like now 14 billion years after the Big Bang. We believe that near the time of the Big Bang, things were so dense and so hot, they were all gaseous. We know that, and the temperatures are humongous, but we know that hot gas radiates. And so the question was, if we saw back far enough, could we actually see this radiation and confirm the fact that this picture is correct? So in fact, astronomers worked with NASA, built a satellite, and realize that picture was valid until about the time the Mount Palomar 200-inch or 5-meter telescope was built, say in the 1950s. So this was a simple cosmological picture that was believed, and the test of it was done through this COBE satellite that was launched in actually November of 1989. I put 1990 here because it observed for a couple of years. And what it tried to do was to measure this background that should be seen everywhere from radiation that occurred 14 billion years ago. So this satellite was built to detect the radiation. Now we know that anytime the so-called Doppler effect is valid for the light from anything in the universe, the galaxies, or this hot gas that we see or hope to see 14 billion light years away. It's expanding away from us, right? Therefore, the wavelength of that gas should be shifted to longer wavelengths, to the red, so-called redshift, in the same way that the sound of an ambulance, you know, is higher in pitch when it's toward you, and as soon as it goes by, then the pitch becomes lower. So this little satellite actually observed sensitively the entire sky to see if it could detect this faint radiation. Now they had to subtract out all of the little point sources, that is, all the light from the stars that happened to be a few other galaxies and the like. So a very complicated process. They did this, and in fact, showed that they could detect what we call now the cosmic background radiation. Very faint. And what's interesting, it coincides with the fact that we seem to be seeing this from a hot gas that was thousands of degrees up in temperature and radiating at a distance of basically 14 billion light years away. The other interesting aspect, so that confirmed the picture, the Big Bang. It just is consistent with it. The other thing that was interesting was they found this radiation to be amazingly homogeneous, just absolutely the same intensity everywhere, to 1 part in 30,000. That is more homogeneous than the air in this room, just remarkably homogeneous, except for tiny fluctuations. I'll throw big words at you, but you know, quantum fluctuations basically. That is, if you plot the intensity of this cosmic microwave background, there were little regions here where the temperature was a bit higher and density either a bit higher or lower that caused this not to be absolutely homogeneous. And that was interesting, sufficiently interesting, in fact, so you point out some of these areas that a Nobel Prize, actually to 2 people, were given because of the success of this project that essentially confirmed the concept of the Big Bang. So, back to this picture. So we still got telescopes here, and from the ground, say the Palomar 5-meter, it could look back maybe this far from where we are in the 14 billion years. Now, we didn't know, of course, we just heard that the amateurs have done. Had everyone looked at the sky like the amateurs did and been able to take spectra, which enables us to determine distances, we would have realized, you know, for a certain few objects, we actually can see objects back here, which is what the Hubble Deep Field is, and that's what I'm getting to. But didn't know that at that time. So here we had, this is our universe now. The COBE satellite indicated that that was the state of the universe within the first 500,000 years after the Big Bang, and 500,000 there is a very small number in cosmic time. And so what's happening here? This was the interesting stuff. We went from this hot gas to these galaxies. So how did large-scale structure form? And that was what people were interested in using Hubble telescope for, and ground-based telescopes if they'd actually been able to achieve this. So, because Hubble telescope had spherical aberration, we basically were not able to make the observations that we wanted to try to get in there and see exactly what did galaxies look like between the hot fog and the current epoch. So theoretical astronomers took over and made predictions about it. We had hoped that the observers would actually get the data first, but because of the spherical aberration, they didn't. And so what the theoretical astrophysicists did is very interesting. And so I'll show you that, but before I do, there's one other concept that you need to know about. That was due to the investigations of some astronomers, Fritz Zwicky initially, but after him, an astronomer who was a good friend of mine, Vera Rubin, who studied the velocities of stars in galaxies, in nearby galaxies, you know, within, say, 10 to 20 million light years. And what Vera did at Kitt Peak National Observatory was actually determining the velocities of stars, trying to use them to determine what the masses of galaxies were. It's an important quantity. If you're studying any object, what's its mass? It's probably the most important quantity that determines the characteristics of any object, whether we're talking planet, star, or galaxy. What Vera found over a number of years was that the stars in the outer parts of the galaxies were much greater than we had anticipated from the brightness of the galaxies, where we assumed what the mass should be. In other words, she found that the velocities of the stars were so great that they shouldn't have escaped being lost from the galaxy. That the gravity of the galaxy was not as large enough based on its light to have kept the stars there. So she posited the thesis that there was material that didn't radiate, therefore you couldn't see it, couldn't detect it through the normal means that astronomers work with, looking at light. And so she posited the existence of dark matter. Now, I shouldn't attribute it only to her, because other people had suggested this, but it was really Vera who confirmed this and put it on such a solid basis. And so that's very important, because it was the existence of this dark matter that was needed for theoretical astronomers to predict exactly how those inhomogeneities in that hot fog might have interacted with each other to produce stars and galaxies, which we know now exist. So I want to pay tribute to Vera, again, a good friend. We first met more than 50 years ago. She was starting her career using the telescopes at Kitt Peak. I was a professor early in my career at the University of Arizona, so we would meet on the mountain and chat. And we went our separate ways. I went down to Chile. She moved to Carnegie Observatories in Washington. When I came up to Space Telescope Science Institute, we reconnected. And we found out somehow that my wife Elaine and Vera's birthday were a day apart and 1 decade apart. And so we thought, let's celebrate our birthdays together. And so on her 80th birthday, which was in 2008, I believe it was, may have been 8 or 9, we were going to have a big celebration. Elaine and I were putting something on for Vera. And sadly, her husband, Bob, died just a few months before that. And I knew Bob because we'd served on some committees together, so we canceled that. But the next year, Vera was up to a celebration, and so there was a large party that we had in Vera's backyard, which is right near Broadbench Road at the Department of Terrestrial Magnetism. And this is a picture of Vera on her 81st birthday, a wonderful person. And I'm happy to tell you that the United States Mint this year is minting 3 1/4 in honor of Vera. So on one, So in 2 months, you'll be carrying around pictures of Vera on one side and George Washington on the other. And not a bad duo. So that concept was used to predict how our universe had evolved. Now, there was one other part of this that was needed, and that was, although Vera really confirmed the existence of dark matter, her measurements did not say anything about its nature. And that was important because we needed to know how the interaction of the dark matter went with normal matter. And in fact, that situation was largely solved by some very important work from people here in Santa Cruz, the former Chancellor, George Blumenthal, and colleagues, Sandy Faber, who is just here, and Joe Premack, who is also here, working with Martin Rees, the Astronomer Royal of the UK. They put out way to go, guys. They put out a very important series of papers in which they posited the nature of dark matter. Totally different from normal matter. You know, normal matter, electrons, protons, neutrons. Something entirely different, not very energetic, doesn't interact with radiation. Most normal matter does. It produces radiation if you give it enough energy. And so in a series of papers, they suggested this particular property for dark matter, and it was based on that people started using supercomputers to take the cosmic background results with those little inhomogeneities and predicting how the universe should evolve. So if I now, and I've got a 17-second video here to show you basically that starts essentially 50 million years after the Big Bang, when the homogeneity is still there, and the universe has cooled down to thousands of degrees from the jillions that it was at the time of the Big Bang. And Jonathan, here we go. So 50 million years, what you're going to see is the time now zipping past until we get to 14 billion. So we start with this hot fog there with tiny inhomogeneities, and then it evolves, and I should never have stopped to say that, and lose. Here we go. So they're inhomogeneities, and notice how areas of higher density attract all this other material to them. Hey, we're already at 10 billion years. And you end up basically with the initial inhomogeneities that were slightly more dense, attracting material, creating these voids, and then producing regions of high density where galaxies and clusters of galaxies form. So that is what the theoretical astronomers predicted for the evolution of the universe. Now, let me try again to focus on, and this may not work, what things looked like about 1 billion years later. Because when I show you some James Webb pictures, this is going to be relevant. Okay, at 1 billion years, you're just starting to get some of these inhomogeneities here that are forming what we call large-scale structure. There's galaxies and clusters of galaxies. But there's not a complete, basically, the voids haven't really been fully constituted, shall we say, yet, nor the higher densities that produce the clusters of galaxies that we now see. And this will be important when we look and see about interpreting pictures from James Webb. So in any event, That is what the expectation was that Hubble Space Telescope might be able to make progress on. So first question one could ask is, at that time, even before Hubble was operating, did this cosmic web, as we call it here, I should have left it there. Love you, Vera. The fact is, the cosmic web, even at that time, had been confirmed. Ground-based telescopes were looking. There were 2 surveys. Center for Astrophysics had one. Again, notice, just about the time of the Blumenthal-Faber Premack papers, mid-1980s. And so this was an observational confirmation of the validity of those theoretical calculations. Now, there have been additional ones. Sloan's Digital Sky Survey, which you already heard about, has filled this in more with lots more observations. And you see that if we were able to take this oversight of the universe, you would see it full of these filaments and voids. So, spherical aberration corrected in the first servicing mission, 1993. And a really good group of young scientists who thought, hey, let's use this to see if there's some confirmation observationally of the details, drilling down into that to see exactly what's happening in those filaments. So when we got together and started talking about the Hubble Deep Field, we picked this undistinguished area of sky. The only photo really of any note was taken as part of a large survey, famous National Geographic Palomar survey taken with a Schmidt on Palomar in the 1950s. So this is what that area looks like when we finally did our 10-day image, okay? And you can see the bright objects here. Here they are. Here's this object there. So the Hubble Deep Field there. Now the question is, what were we able to make from this field? It is a pretty picture, actually. I've got to admit, I still enjoy looking at it. But all it is a pretty picture unless you know what the distances to the objects in that are. And we did that. What you do is you need to know their velocity because of the expanding universe. And so prior to taking this image, we contacted Keck Observatory astronomers, and Keck now, an important part of the University of California Observatories, whose headquarters is just up the campus here. Okay, Keck had just come online, and so there were astronomers from University of Hawaii, which got 10%, and then shared at around 40%, University of California and Caltech. And so we told them about our wish to do this, and they needed to take spectra of the brightest objects in the field here. And so they did that over a period of 3 years. And so the 125 brightest objects in this field have had spectra taken, meaning we know what their velocities are, and therefore we know what their distances are. And so to no surprise, these are relatively nearby galaxies. But a lot of these faint ones, some of them are nearby and very small, not very luminous, but some of them are really far away. And so what we've learned from the deep field, and I'll just put this in this slide, really give you the synopsis of the results. If you look, first of all, at the galaxies that are near us, to no surprise, they're larger. Some of them are bluish, some of them are reddish. And generally that means the same thing as those stars that I showed you before, red and blue. Usually if you have a blue star, that means it's young because they're very massive, they're very luminous, they burn out their energy more quickly. And so they tend to be younger objects because then they explode and you don't see them anymore if they become supernovae. So red stars, on the other hand, usually are stars that, like the sun, may have formed long ago and are not very active now. They're cooler, and therefore they get this reddish color. In any event, stars at the current epoch of our universe, nowadays, tend to be larger. They tend to be symmetric, either spiral structure like our own galaxies, or at least elliptical and nice, smoothly symmetric. On the other hand, if you look at the distant galaxies, 12 billion light years distant, so 12 billion out of the 14, the Hubble time, what you see are a mishmash of galaxies. They tend to be bluish in color. They're smaller than the current galaxies, and they're chaotic. They don't have this symmetric structure. Also, you tend to find them in clumps, and our belief is, in fact, that what you're seeing there in the lower picture are what we call proto-galaxies, smaller clumps that are part of that inhomogeneous structure in the early fog that have started to condense, and the gravitational attraction is working to bring clumps together so that they merge and eventually, after billions of years, grow into the large galaxies. And it is, again, this concept, I don't want to introduce too many concepts. Angular momentum, that is, when you have objects merging together with a particular velocity, it's angular momentum, this angular motion is conserved. And so this chaotic structure in the process of merging is what produces this nice symmetric structure years later. And so this basically is assuming now the validity of the picture of the cold dark matter. That was the Blumenthal et al. Hypothesis. And the observations of the Hubble Deep Field do indicate this basic structure that we had posited is valid. So everything looked cool, actually. Now, there are always puzzles about some of the details. But Hubble isn't the only telescope up there. There's this other telescope. So here is the same area of sky that Hubble took, part of it, one of its deep fields, because it's had now multiple deep fields. Same area of the sky, Hubble in 8 days, Webb in 8 hours. Yeah, impressive. And by the way, you can always tell a Hubble image from the 4 spikes because of the nature of the strut that holds this secondary mirror, as opposed to the more complicated strut that holds the secondary mirror of James Webb, which has 3 of them. And so if there's 6 spikes, that's James Webb. If it's 4, it's Hubble. In any event, you see more on the right for various reasons. Webb is larger, and Webb is an infrared telescope. It looks at the longer wavelengths. And so if you're looking at the distant galaxies, all those waves are shifted to the red. And so the fact is, for both those reasons, Webb is a better telescope to use to try to determine whatever the characteristics of distant objects. So it's had some deep fields. And I'll just show you here in the last couple of slides what it shows. And it's showed some surprises. So here we have part of that same field, and I'll just show you can not really see it, but there are some tiny galaxies there. And if you can read this, maybe you can't. In fact, I think it was Steve already made mention to this. So there are 4 objects here, and there are probably more, but at the time that this was put out, these were the only ones that had been measured at that time. So this object is seen at a distance 13.1 billion years. Remember, if we take 13.8 billion, that means this is 800 million years after the Big Bang. Okay, this is 13.0, so that's around the same. 12, this is a youngster, 12.6, and 11.3. Okay, so that's 2 billion years after the Big Bang. So you can see, and these galaxies look reddish, not bluish. It's artificial. That's because this is an infrared telescope. And so when they put this out, because they are looking in the red, they tend to make it a red color. And so don't be entirely deceived. The color isn't really the same as your eye would see. And in fact, there are some blue objects here, but they're probably at totally different distances and unrelated to these central objects. In any event, the point is, Webb is seeing a long ways away. No surprise. And here are some really important ones. Okay, in this particular deep field, which is a different one, you see a galaxy 450. Okay, 500 million years after the Big Bang, 1/3 of a billion, 350 million after the Big Bang. In other words, galaxies were there, and these particular objects actually have a luminosity and energy that is much greater than we can account for in those calculations that I showed you. Remember, when I showed the picture of the evolving universe, theoretically, and pointed at what it was like, the cosmic web, which had not really formed very well yet, at 1 billion years, we're seeing galaxies now that are already in existence, very luminous, and probably sufficiently luminous, have characteristics that lead us to believe there are massive black holes in them. And so this is not what we would have expected based on our calculations. And so the current concept of the nature of cold dark matter is one that is in question. Well, it's images such as this that basically are the legacy of the deep field and deep fields of both Hubble and James Webb. And it's causing scientific inquiry in this subject to be really impressive. So let me end by saying that as important as the deep fields have been to science, the deep fields have worked their way into other parts of society's interests. And I want to give you some interesting examples. One of them, a contemporary American composer, Eric Whitacre, was taken by an image of the deep field, and he wanted to compose a piece for it. Minnesota Orchestra had commissioned him to do a work together with the famous London Proms concerts that are conducted late summer each year. So they got together, and Eric decided to write a piece basically that reflects in a chromatic way sound his understanding of our search for distant galaxies and then our finding of it. And the deep field, basically, it's a neat performance. There's one other thing I forgot to say. Let me go back because it's a very important part of the deep fields. And that is, we can determine by comparing the brightnesses of stars long ago that are very bluish, massive, and just formed with the brightness and luminosities of stars in the current era of the universe. And the whole history of star formation we have determined from this. And basically what it is it turns out that stars began to form about the time that you see these galaxies here, 1 billion or 2 years, and there's a lot of uncertainty, after the Big Bang, stars started to form. At a time about halfway between now and the Big Bang, that is around 7 billion years ago, it turns out from images, again, in the deep field, star formation had increased. They were making available, of course, the gas that was there from the Big Bang, converting that gas into stars. So there was a very large rate of star formation at 7 billion years, And in the current epoch, we're finding a star formation to have decreased again. Most of the gas is used up. So it's very interesting. If I just plotted simply star formation rate as a function of time, it ramps up after the Big Bang when the universe has cooled off and these proto-galaxies are forming. Then about halfway, 7 billion years later, it peaks. And then as the gas is used up, and also because of the lower density from the expanding universe, it disadvantages, to a certain extent, star formation. It dips down. Point, we're living in a dying universe. Most of the stars have formed, and many of them exploded, or just sitting there, essentially not in nuclear fusion, white dwarf, something like cooling off. So we're living in a dying universe. Don't let it bother you. Billions of years. Oh, and the other thing I should say about Eric Whittaker, if you look at this, it's on YouTube. The performance that he gave at the London Proms has 8 million views. So he's getting up there toward Beyonce. I have found that in discussions written, the universal values and philosophy, you frequently find images of the deep field for reasons that are, this is where we came from. And so you find that. There's a play about the deep field. It's called Redshift. And it highlights the work of an autistic cosmologist, on the spectrum, who finds out about the deep field and makes some important discoveries from it. It's been playing in planetaria, and Chalmers, the author, who I know, I advised him on this, is seeing if he can get this on off-Broadway. And then finally, we've got the amateurs who are turned on by this and have done their own deep fields, and you've just seen that they've found an object that is amazingly far away for the size of the telescopes that found it. So this is the legacy of the deep fields. They still generate interest in humanity, and one could wonder why. But to me, I would say that our real interest in trying to understand an image like the deep field, it's in our DNA, really, because when you look at it, you're seeing all those galaxies, stars, planets, humanity, which formed from it, and us. So the next time you see an image of the deep field, realize that really you're looking at a selfie of us. And that is the true value of the Hubble Deep Field. Thank you.